Let's say you work at a bank. Today, your task is to train a classifier that can recognize counterfeit bills. A steady stream of money is going to be fed into your system, and your new model will need to flag the suspicious notes immediately. Here's the question. How would you train this type of system? Intuitively, you'd probably say that you take one stack of counterfeit bills and another stack of regular bills. Label both stacks and train your system on both. Once the model has seen example after example, it should learn to identify the patterns and hallmarks that indicate a fake, as well as the features and consistencies that prove something is real. Pretty straightforward, no? Okay. Well, let's make this example a little bit more complicated then. Let's say that instead of handing you a stack of real bills and a stack of fake bills, I hand you stacks that are mixes of both. I say, this is stack A. It has 35% fake bills and 65% real bills. And this is stack B. It has the reverse, 65% fake and 35% real. I haven't told you which individual bills are good and which are bad, only the overall mixture of the stacks. Now, what would you do? Well, all you can do is train a classifier that learns to distinguish stack A from stack B. Instead of learning that a given bill is more or less likely to be counterfeit, it learns that a given bill is more or less likely to belong to one stack or the other. This might sound like a fundamentally different job for the classifier, but guess what? It is actually mathematically equivalent to the first example. We call this a monotonic transformation. The problem shifts from directly separating counterfeit bills from real ones to separating one mixed population from another. But in the end, it is still evaluating bills on how signal-like they are. When one stack has a higher fraction of counterfeits than the other, any feature that makes a bill more likely to come from that stack also makes it more likely to be counterfeit. And any feature that makes it more likely to come from the other stack pushes in the opposite direction. The system is still effectively learning to spot the same signals and background patterns. The problem is just framed in a different way. So, why did I just tell you all this? Well, because monotonic transformations are key to what they're doing in this paper. Strong CWoLa, binary classification without background simulation. They're doing the same thing we just talked about, but for particle physics. Instead of developing a model that can identify fake bills and stacks of good ones, they are building a model that can identify rare physics signals in huge piles of background data. This is essentially the same job, just a different context. On today's episode of Journal Club, we're going to explain all of it. The whole paper, everything the authors did, why they did it, and the results they obtained. If you're already subscribed to our email newsletter, then you'll be getting this episode in text, audio, and video form delivered to your inbox in the next few hours. Journal Club, the latest academic research explained in plain English.